Good morning, students. Today we will going to discuss about the post office box experiment. So using this apparatus setup, we will going to determine the band gap of this semiconductor. Actually, this is one of the semiconductor. It's a thermistor. Okay, and to determine the band gap of this thermistor, and we have an apparatus setup, and in which. So in this apparatus setup, it is a battery which produces a power of 2 volt, and this is our main apparatus PO box, and we have a galvanometer. And in this PO box, there is a B terminal is connected to the battery and the G terminals are connected to the galvanometer. On this X is an unknown resistance, it's a thermistor, and it is simply a Weinstein bridge. So I think you know about the Weinstein bridge. There is a 4 resistance are connected, and the 2 points are connected with the power supply. On the other 2 points are connected with the galvanometer, and this is P, Q, R, S. So this is a simple Weinstein bridge. And there will be a condition to get a null deflection in your galvanometer. So the null deflection condition is P by Q is equal to R by S. P by Q is equal to R by S. And in this apparatus setup, here we have a P dial here, and this is Q dial. So this is a P resistance and Q resistance, and these 4 dials are together, it is a R. And instead of S, we are connected here, there is a thermistor, it's an unknown resistance. So to find the unknown resistance, so we can rearrange this formula. So S is an unknown resistance, which is equal to Q by P into R. Q by P into R. So we said this is a X. T is a total resistance, is a Q by P into R. Okay, so at each and every temperature, we have to nullify the galvanometer to measure the resistance of the thermistor, because a thermistor is a material which shows a different resistance at a different temperature. So in this apparatus setup, we will going to find out the resistance of the thermistor at different temperature. Okay, so we raise the temperature nearly 100 degrees centigrade or 90 degrees centigrade, and we insert our thermistor inside this oil. So this is the transformer oil, and it can able to withstand for high temperature. That's why we use this oil, and we insert the thermistor into the oil, and there will be a thermometer which shows the corresponding temperature. Now it is nearly 83 temperature. I'm going to start at 80. So at 80 we have to measure how much resistance in this dial. So to measure the resistance, to connect the circuit, just we have to press these 2 buttons, and the galvanometer will show us a deflection, and we have to nullify the galvanometer by adjusting these values of R. That means this dials. So I increase the 100 and this 2. Now it is completely 0. So at 80 degrees Celsius, and I got the resistance R value 300 to 10. That is 320, and these 2 are 0. So the total resistance value will be 320. And before that, I fixed this P dial as 100. This is a P dial, I said, no? This is P dial as 100 resistance, and Q dial is 10 resistance. So it is constant. So we don't bother about the other values. We are going to take the P value on the tabular column as 100, and Q value is 10. At this condition, we got the R value is 320 to nullify the galvanometer. Similarly, we have to take the reading at 75 degrees centigrade. Now, I think we got 75 here. So same way, press the 2 buttons, and now the galvanometer will show us the deflection. To nullify the deflections, again adjust this, increase the resistance on the R dial to make 0 on your galvanometer. Now find out what is the resistance here. Now the same is a 360. So for 75 degrees centigrade, It is 360. Clear? Okay, and wait for some time to reach 70. At 70, we have to again nullify the galvanometer. Now the temperature is 70. Again, I have to press this 2 button. Now your galvanometer will show deflection. So by increasing the resistance on this dial, I have to make the null deflection in your galvanometer. Now the resistance is 390. 390 against 70 degrees centigrade. Okay. Stop now. Okay, so now we are going to reach the 65 now. Again, now press this button. There is a deflection. So I have to increase the resistance on this 10 dial, but this is a maximum value. So we can reach the maximum value here. So just reduce this into 0, 10, and just increase the 100 in 1. So now the same position will be here. Again, you have to increase this 10 resistance. And at particular position, we have null deflection, and find out what is the corresponding resistance here. So 450. So that for 65 degree centigrade, we got 450 on your all dial. Similarly, we can able to take all other values for 60 as well as 55. So similarly, we can able to write for 60 as well as 55, and we got these readings for these values, R values. Using this R value, we can able to find the value of XT, that is unknown resistance for this given condition. So just substitute this formula already we discussed to find the XT value. It is a Q by P into R. So substitute this condition over here, and you can able to find the unknown resistance for each and every temperature. And then after, it is a simple calculation. Convert this temperature in Celsius to Kelvin and convert the Kelvin as a 1 by T. Find out the 1 by T value. So it becomes 3.48 into 10 power 3, and the 10 power 3 I commonly wrote here as a 10 power 3. It's common for all. And then similarly, using this XT value, I substitute over here 2.303 log base 10 of XT. So just find the log of 55, multiply with 2.303, and you will get the answer. So these are all the values of 2.303 log base 10 of RT for every resistance of R with the corresponding temperature, and these are all the corresponding temperature, inverse of temperature. Now using these two data, we are going to draw a graph, and this is a graph. Along the x-axis we took 1 by T, this 1 by T, and along the y-axis we take 2.303 log base 10 of RT, that means XT. So using the given data, we calculated data, and we can draw the graph, and the graph will become a straight line. And find the slope of the curve. The slope will indicate the slope of the graph, which says that variation of y-axis divided by variation along x-axis. So that is the slope. And just substitute the slope value on this formula. The formula is 2k into 2.303 log base 10 of, what is it, xt divided by 1 by t. So this we got it from the graph, slope. So this is the slope of the curve, and just multiply the slope with the 2 into k, where k is the Boltzmann constant, and that value is known. K is the Boltzmann constant. Is a Boltzmann constant as a 1.38 into 10 to the power minus 23. This is the value of k, and multiply the slope. We got the slope value as slope value into 10 power 3. So the formula is to find the band gap 2k into 2.303 log base 10 of xt by 1 by t. So this is a slope of the graph. So we can write as a 2k into slope. And from the slope we got is a 2.5 10 power 3. So this is the slope of the straight line. And the k value is 1.38 in 10 power minus 23. So by multiplying this all those values, you will get Eg is equal to 6.9 into 10 to the power minus 20 in terms of joule. But mostly we are express the band gap in terms of electron volt. So to convert the joule into electron volt, just divided by the charge of the electron, 1.6 into 10 power minus 19. So after dividing that, you will get the final value of band gap of the thermistor as a 0.428 electron volt. Okay, I think it's clear. Thank you, students.